Good evening, and thank you for joining me for another Boring Books for Bedtime. I hope tonight's selection provides all the boredom your busy brain needs to quiet down and let you get some sleep. Before we begin, I'd like to give a special shout out of thanks to some new members of our Patreon family: Stephanie, Chris, Sean, Lindsay, and Windowbird. Thank you all so much for supporting this podcast. By becoming members of Patreon, you help us remain ad-free and relaxed for everyone, and it's very much appreciated. And because you joined us in the month of November, you and everyone else who supports us by becoming a member of Patreon or dropping us a one-time tip via buymeacoffee.com will be entered into our first raffle in some time, the prize for which is an episode of Boring Books for Bedtime made just for you. And because it's just for you, copyright restrictions do not apply. So if you've always wanted to hear the joy of cooking or a brief history of everything, this is your chance. You'll find links to both Patreon and buymeacoffee.com in the show description. Good luck to everyone, and thank you for supporting. Now, let's read and relax. Find a comfortable spot. Adjust your volume. Take a nice deep breath in. Let it out slowly. And off we go. Tonight we return to the relaxing world of science with more from the ABC of Relativity by Bertrand Russell, author of The Principles of Mathematics, Proposed Roads to Freedom, and Why Men Fight. First published in 1925 by Harper & Brothers of New York and London. Let's pick up right where we left off with Chapter 3, The Velocity of Light. Let's begin. Chapter 3, The Velocity of Light. Most of the curious things in the theory of relativity are connected with the velocity of light. If the reader is to grasp the reasons for such a serious theoretical reconstruction, he must have some idea of the facts which made the old system break down. The fact that light is transmitted with a definite velocity was first established by astronomical observations. Jupiter's moons are sometimes eclipsed by Jupiter, and it is easy to calculate the times when this ought to occur. It was found that when Jupiter was unusually near the Earth, an eclipse of one of his moons would be observed a few minutes earlier than was expected, and when Jupiter was unusually remote, a few minutes later than was expected. It was found that these deviations could all be accounted for by assuming that light has a certain velocity, so that what we observe to be happening in Jupiter really happened a little while ago, longer ago when Jupiter is distant than when it is near. Just the same velocity of light was found to account for similar facts in regard to other parts of the solar system. It was therefore accepted that light in vacuo always travels at a certain constant rate, almost exactly 300,000 kilometers a second. A kilometer is about 5/8 of a mile. When it became established that light consists of waves, this velocity was that of propagation of waves in the ether. At least they used to be in the ether, but now the ether has grown somewhat shadowy, though the waves remain. This same velocity is that of the waves used in wireless telegraphy, which are like light waves, only longer, and in X-rays, which are like light waves, only shorter. It is generally held nowadays to be the velocity with which gravitation is propagated, though Eddington considers this not yet certain. It used to be thought that gravitation was propagated instantaneously, but this view is now abandoned. So far, all is plain sailing, but as it became possible to make more accurate measurements, difficulties began to accumulate. The waves were supposed to be in the ether, and therefore their velocity ought to be relative to the ether. Now, since the ether, if it exists, clearly offers no resistance to the motions of the heavenly bodies, it would seem natural to suppose that it does not share their motion. If the earth had to push a lot of ether before it, in the sort of way that a steamer pushes water before it, one would expect a resistance on the part of the ether, analogous to that offered by the water to the steamer. Therefore, the general view was that the ether could pass through bodies without difficulty, like air through a coarse sieve, only more so. If this were the case, then the Earth in its orbit must have a velocity relative to the ether. If at some point of its orbit it happened to be moving exactly with the ether, it must at other points be moving through it all the faster. If you go for a circular walk on a windy day, you must be walking against the wind part of the way, whatever wind may be blowing. The principle in this case is the same. It follows that if you choose 2 days 6 months apart, when the Earth in its orbit is moving in exactly opposite directions, it must be moving against an ether wind on at least one of these days. Now, if there is an ether wind, it is clear that, relatively to an observer on the Earth, light signals will seem to travel faster with the wind than across it, and faster across it than against it. This is what Michelson and Morley set themselves to test by their famous experiment. They sent out light signals in 2 directions at right angles. Each was reflected from a mirror and came back to the place from which both had been sent out. Now anybody can verify, either by trial or by a little arithmetic, that it takes longer to row a given distance on a river upstream and then back again than it takes to row the same distance across the stream and back again. Therefore, if there were an ether wind, one of the 2 light signals, which consist of waves in the ether, ought to have traveled to the mirror and back at a slower average rate than the other. Michelson and Morley tried the experiment. They tried it in various positions. They tried it again later. Their apparatus was quite accurate enough to have detected the expected difference of speed, or even a much smaller difference if it had existed, but not the smallest difference could be observed. The result was a surprise to them as to everybody else, but careful repetitions made doubt impossible. The experiment was first made as long ago as 1881 and was repeated with more elaboration in 1887, but it was many years before it could be rightly interpreted. The supposition that the Earth carries the neighboring ether with it in its motion was found to be impossible for a number of reasons. Consequently, a logical deadlock seemed to have arisen, from which at first physicists sought to extricate themselves by very arbitrary hypotheses. The most important of these was that of Fitzgerald, developed by Lorentz, and known as the Fitzgerald contraction hypothesis. According to this hypothesis, when a body is in motion, it becomes shortened in the direction of motion by a certain proportion depending upon its velocity. The amount of the contraction was to be just enough to account for the negative result of the Michelson-Morley experiment. The journey upstream and down again was to have been really a shorter journey than the one across the stream, and was to have been just so much shorter as would enable the slower light wave to traverse it in the same time. Of course, the shortening could never be detected by measurement because our measuring rods would share it. A foot rule placed in the line of the Earth's motion would be shorter than the same foot rule placed at right angles to the Earth's motion. This point of view resembles nothing so much as the white knights planned to dye my whiskers green and always use so large a fan that they could not be seen. The odd thing was that the plan worked well enough. Later on, when Einstein propounded his special theory of relativity in 1905, it was found that the theory was, in a certain sense, correct, but only in a certain sense. That is to say, the supposed contraction is not a physical fact, but a result of certain conventions of measurement, which, when once the right point of view has been found, are seen to be such as we are almost compelled to adopt. But I do not wish yet to set forth Einstein's solution of the puzzle. For the present, it is the nature of the puzzle itself that I want to make clear. On the face of it, and apart from hypotheses ad hoc, the Michelson-Morley experiment, in conjunction with others, showed that relatively to the Earth, the velocity of light is the same in all directions, and that this is equally true at all times of the year, although the direction of the Earth's motion is always changing as it goes round the sun. Moreover, it appeared that this is not a peculiarity of the Earth, but is true of all bodies. If a light signal is sent out from a body, that body will remain at the center of the waves as they travel outwards, no matter how it may be moving. At least, that will be the view of observers moving with the body. This was the plain and natural meaning of the experiments, and Einstein succeeded in inventing a theory which accepted it. But at first it was thought logically impossible to accept this plain and natural meaning. A few illustrations will make it clear how very odd the facts are. When a shell is fired, it moves faster than sound. The people at whom it is fired first see the flash, then, if they are lucky, see the shell go by, and last of all hear the report. It is clear that if you could put a scientific observer on the shell, he would never hear the report, as the shell would burst and kill him before the sound had overtaken him. But if sound worked on the same principles as light, our observer would hear everything just as if he were at rest. In that case, if a screen suitable for producing echoes were attached to the shell and traveling with it, say 100 yards in front of it, our observer would hear the echo of the report from the screen after just the same interval of time as if he and the shell were at rest. This, of course, is an experiment which cannot be performed, but others which can be performed will show the difference. We might find some place on a railway where there is an echo from a place further along the railway, say a place where the railway goes into a tunnel. And when a train is traveling along the railway, let a man on the bank fire a gun. If the train is traveling towards the echo, the passengers will hear the echo sooner than the man on the bank. If it is traveling in the opposite direction, they will hear it later. But these are not quite the circumstances of the Michelson-Morley experiment. The mirrors in that experiment correspond to the echo, and the mirrors are moving with the earth, so that echo ought to move with the train. Let us suppose that the shot is fired from the guard's van, and the echo comes from a screen on the engine. We will suppose the distance from the guard's van to the engine to be the distance that sound can travel in a second, about 1/5 of a mile, and the speed of the train to be 1/12 of the speed of sound, about 60 miles an hour. We now have an experiment which can be performed by the people in the train. If the train were at rest, the guard would hear the echo in 2 seconds. As it is, he will hear it in 2 143rds seconds. From this difference, if he knows the velocity of sound, he can calculate the velocity of the train, even if it is a foggy night, so that he cannot see the banks. But if sound behaved like light, he would hear the echo in 2 seconds, however fast the train might be traveling. Various other illustrations will help to show how extraordinary, from the point of view of tradition and common sense, are the facts about the velocity of light. Everyone knows that if you are on an escalator, you reach the top sooner if you walk up than if you stand still. But if the escalator moved with the velocity of light, which it does not do even in New York, you would reach the top at exactly the same moment whether you walked up or stood still. Again, if you are walking along a road at the rate of 4 miles an hour, and a motor car passes you going in the same direction at the rate of 40 miles an hour, if you and the motor car both keep going, the distance between you after an hour will be 36 miles. But if the motor car met you going in the opposite direction, the distance after an hour would be 44 miles. Now, if the motor car were traveling with the velocity of light, it would make no difference whether it met or passed you. In either case, it would, after a second, be 186,000 miles from you. It would also be 186,000 miles from any other motor car which happened to be passing or meeting you less rapidly at the previous second. This seems impossible. How can the car be at the same distance from a number of different points along the road? Let us take another illustration. When a fly touches the surface of a stagnant pool, it causes ripples which move outwards in widening circles. The center of the circle at any moment is the point of the pool touched by the fly. If the fly moves about over the surface of the pool, it does not remain at the center of the ripples. But if the ripples were waves of light and the fly were a skilled physicist, it would find that it always remained at the center of the ripples, however it might move. Meanwhile, a skilled physicist sitting beside the pool would judge, as in the case of ordinary ripples, that the center was not the fly, but the point of the pool touched by the fly. And if another fly had touched the water at the same spot at the same moment, it also would find that it remained at the center of the ripples, even if it separated itself widely from the first fly. This is exactly analogous to the Michelson-Morley experiment. The pool corresponds to the ether. the fly corresponds to the earth. The contact of the fly and the pool corresponds to the light signal which Messrs. Michelson and Morley sent out, and the ripples correspond to the light waves. Such a state of affairs seems at first sight quite impossible. It is no wonder that, although the Michelson-Morley experiment was made in 1881, it was not rightly interpreted until 1905. Let us see what exactly we have been saying. Take the man walking along a road and passed by a motor car. Suppose there are a number of people at the same point of the road, some walking, some in motor cars. Suppose they are going at varying rates, some in one direction and some in another. I say that if, at this moment, a light flash is sent out from the place where they all are, the light waves will be 186,000 miles from each one of them after a second by his watch, although the travelers will not any longer be all in the same place. At the end of a second by your watch, it will be 186,000 miles from you, and it will also be 186,000 miles from a person who met you when it was sent out but was moving in the opposite direction after a second by his watch, assuming both to be perfect watches. How can this be? There is only one way of explaining such facts, and that is to assume that watches and clocks are affected by motion. I do not mean that they are affected in ways that could be remedied by greater accuracy in construction. I mean something much more fundamental. I mean that if you say an hour has elapsed between two events, and if you base this assertion upon ideally careful measurements with ideally accurate chronometers, another equally precise person who has been moving rapidly relative to you may judge that the time was more or less than an hour. You cannot say that one is right and the other wrong, any more than you could if one used a clock showing Greenwich time and another a clock showing New York time. How this comes about, I shall explain in the next chapter. There are other curious things about the velocity of light. One is that no material body can ever travel as fast as light, however great may be the force to which it is exposed, and however long the force may act. An illustration may help to make this clear. At exhibitions, one sometimes sees a series of moving platforms going round and round in a circle. The outside one goes at 4 miles an hour. The next goes 4 miles an hour faster than the first, and so on. You can step across from each to the next until you find yourself going at a tremendous pace. Now you might think that if the first platform does 4 miles an hour, and the second does 4 miles an hour relatively to the first, then the second does 8 miles an hour relatively to the ground. This is an error. It does a little less, though so little less that not even the most careful measurements could detect the difference. I want to make quite clear what it is that I mean. I will suppose that in the morning, when the apparatus is just about to start, 3 men with ideally accurate chronometers stand in a row, one on the ground, one on the first platform, and one on the second. The first platform moves at the rate of 4 miles an hour with respect to the ground. 4 miles an hour is 352 feet in a minute. The man on the ground, after a minute by his watch, notes the place on the ground opposite the man on the first platform, who has been standing still while the platform carried him along. The man on the ground measures the distance on the ground from himself to the point opposite the man on the first platform, and finds it is 352 feet. The man on the first platform measures the distance from himself to the point opposite the man on the second platform. It is again 352 feet. Problem: how far will the man on the ground judge that the man on the second platform has traveled in a minute? That is to say, if the man on the ground, after a minute by his watch, notes the place on the ground opposite the man on the second platform, how far will this be from the man on the ground? You would say twice 352 feet. That is to say, 704 feet. But in fact it will be a little less, though so little less as to be inappreciable. The discrepancy is owing to the fact that the two watches do not keep perfect time, in spite of the fact that each is accurate from its owner's point of view. If you had a long series of such moving platforms, each moving 4 miles an hour relatively to the one before it, you would never reach a point where the last was moving with the velocity of light relatively to the ground, not even if you had millions of them. The discrepancy, which is very small for small velocities, becomes greater as the velocity increases, and makes the velocity of light an unattainable limit. How all this happens is the next topic with which we must deal. Note: the negative result of the Michelson-Morley experiment has recently been called in question by Professor Dayton C. Miller as a result of observations by what is said to be an improved method. His claim is set forth by Professor Silberstein in Nature, May 23, 1925, and discussed unfavorably by Eddington in the issue of June 6. The matter is under review, but it seems highly questionable whether the results bear out the interpretation which is put upon them. Chapter 4: Clocks and Foot Rules. Until the advent of the special theory of relativity, no one had thought that there could be any ambiguity in the statement that two events in different places happened at the same time. It might be admitted that, if the places were very far apart, there might be difficulty in finding out for certain whether the events were simultaneous, but everyone thought the meaning of the question perfectly definite. It turned out, however, that this was a mistake. Two events in distant places may appear simultaneous to one observer who has taken all due precautions to ensure accuracy, and in particular has allowed for the velocity of light, while another equally careful observer may judge that the first event preceded the second, and still another may judge that the second preceded the first. This would happen if the three observers were all moving rapidly relatively to each other. It would not be the case that one of them would be right and the other two wrong. They would all be equally right. The time order of events is in part dependent upon the observer. It is not always and altogether an intrinsic relation between the events themselves. Einstein has shown not only that this view accounts for the phenomena, but also that it is the one which ought to have resulted from careful reasoning based upon the old data. In actual fact, however, no one noticed the logical basis of the theory of relativity until the odd results of experiment had given a jog to people's reasoning powers. How should we naturally decide whether two events in different places were simultaneous? One would naturally say they are simultaneous if they are seen simultaneously by a person who is exactly halfway between them. There is no difficulty about the simultaneity of two events in the same place, such, for example, as seeing a light and hearing a noise. Suppose two flashes of lightning fall in two different places, say Greenwich Observatory and Kew Observatory. Suppose that St. Paul's is halfway between them and that the flashes appear simultaneous to an observer on the dome of St. Paul's. In that case, a man at Kew will see the Kew flash first, and a man at Greenwich will see the Greenwich flash first, because of the time taken by light to travel over the intervening distance. But all three, if they are ideally accurate observers, will judge that the two flashes were simultaneous, because they will make the necessary allowance for the time of transmission of the light. I am assuming here a degree of accuracy far beyond human powers. Thus, so far as observers on the earth are concerned, the definition of simultaneity will work well enough, so long as we are dealing with events on the surface of the earth. It gives results which are consistent with each other and can be used for terrestrial physics in all problems in which we can ignore the fact that the earth moves. But our definition is no longer so satisfactory when we have two sets of observers in rapid motion relatively to each other. Suppose we see what would happen if we substitute sound for light and defined two occurrences as simultaneous when they are heard simultaneously by a man halfway between them. This alters nothing in the principle, but makes the matter easier, owing to the much slower velocity of sound. Let us suppose that on a foggy night, two men belonging to a gang of brigands shoot the guard and engine driver of a train. The guard is at the end of the train. The brigands are on the line and shoot their victims at close quarters. An old gentleman who is exactly in the middle of the train hears the two shots simultaneously. You would say, therefore, that the two shots were simultaneous. But a station master who is exactly halfway between the two brigands hears the shot which kills the guard first. An Australian millionaire uncle of the guard and the engine driver, who are cousins, has left his whole fortune to the guard, or, should he die first, to the engine driver. Vast sums are involved in the question of which died first. The case goes to the House of Lords, and the lawyers on both sides, having been educated at Oxford, are agreed that either the old gentleman or the station master must have been mistaken. In fact, both may perfectly well be right. The train travels away from the shot at the guard and towards the shot at the engine driver. Therefore, the noise of the shot at the guard has farther to go before reaching the old gentleman than the shot at the engine driver has. Therefore, if the old gentleman is right in saying that he heard the two reports simultaneously, the station master must be right in saying that he heard the shot at the guard first. We who live on the earth would naturally, in such a case, prefer the view of simultaneity obtained from a person at rest on the earth to the view of a person traveling in a train. But in theoretical physics, no such parochial prejudices are permissible. A physicist on a comet, if there were one, would have just as good a right to his view of simultaneity as an earthly physicist has to his, but the results would differ in just the same sort of way as in our illustration of the train and the shots. The train is not any more really in motion than the earth. There is no really about it. You might imagine a rabbit and a hippopotamus arguing as to whether man is really a large animal. Each would think his own point of view the natural one, and the other a pure flight of fancy. There is just as little substance in an argument as to whether the earth or the train is really in motion, and therefore when we are defining simultaneity between distant events, we have no right to pick and choose among different bodies to be used in defining the point halfway between the events. All bodies have an equal right to be chosen. But if for one body the two events are simultaneous according to the definition, there will be other bodies for which the first precedes the second, and still others for which the second precedes the first. We cannot therefore say unambiguously that two events in distant places are simultaneous. Such a statement only acquires a definite meaning in relation to a definite observer. It belongs to the subjective part of our observation of physical phenomena, not to the objective part, which is to enter into physical laws. The question of time in different places is perhaps for the imagination the most difficult aspect of the theory of relativity. We are accustomed to the idea that everything can be dated. Historians make use of the fact that there was an eclipse of the sun visible in China on August 29th in the year 776 BC. No doubt astronomers could tell the exact hour and minute when the eclipse began to be total at any given spot in North China, and it seems obvious that we can speak of the positions of the planets at a given instant. The Newtonian theory enables us to calculate the distance between the Earth and, say, Jupiter at a given time by the Greenwich clocks. This enables us to know how long light takes at that time to travel from Jupiter to the Earth, say half an hour. This enables us to infer that half an hour ago, Jupiter was where we see it now. All this seems obvious, but in fact it only works in practice because the relative velocities of the planets are very small compared with the velocity of light. When we judge that an event on the Earth and an event on Jupiter have happened at the same time, for example, that Jupiter eclipsed one of his moons when the Greenwich clocks showed 12 midnight, a person moving rapidly relative to the Earth would judge differently, assuming that both he and we had made the proper allowance for the velocity of light. And naturally, the disagreement about simultaneity involves a disagreement about periods of time. If we judge that two events on Jupiter were separated by 24 hours, another person might judge that they were separated by a longer time if he were moving rapidly relatively to Jupiter and the Earth. The universal cosmic time, which used to be taken for granted, is thus no longer admissible. For each body, there is a definite time order for the events in its neighborhood. This may be called the proper time for that body. Our own experience is governed by the proper time for our own body. As we all remain very nearly stationary on the earth, the proper times of different human beings agree and can be lumped together as terrestrial time. But this is only the time appropriate to large bodies on the earth. For beta particles in laboratories, quite different times would be wanted. It is because we insist upon using our own time that these particles seem to increase in mass with rapid motion. From their own point of view, their mass remains constant, and it is we who suddenly grow thin or corpulent. The history of a physicist as observed by a beta particle would resemble Gulliver's Travels. The question now arises, what really is measured by a clock? When we speak of a clock in the theory of relativity, we do not mean only clocks made by human hands. We mean anything which goes through some regular periodic performance. The Earth is a clock because it rotates once in every 23 hours and 56 minutes. An atom is a clock because the electrons go round the nucleus a certain number of times in a second. Its properties as a clock are exhibited to us in its spectrum, which is due to light waves of various frequencies. The world is full of periodic occurrences, and fundamental mechanisms such as atoms show an extraordinary similarity in different parts of the universe. Any one of these periodic occurrences may be used for measuring time. The only advantage of humanly manufactured clocks is that they are specially easy to observe. One question is, if cosmic time is abandoned, what is really measured by a clock in the wide sense that we have just given to the term? Each clock gives a correct measure of its own proper time, which, as we shall see presently, is an important physical quantity, but it does not give an accurate measure of any physical quantity connected with events on bodies that are moving rapidly in relation to it. It gives one datum towards the discovery of a physical quantity connected with such events. But another datum is required, and this has to be derived from measurement of distances in space. Distances in space, like periods of time, are in general not objective physical facts, but partly dependent upon the observer. How this comes about must now be explained. First of all, we have to think of the distance between two events, not between two bodies. This follows at once from what we have found as regards time. If two bodies are moving relatively to each other, and this is really always the case, the distance between them will be continually changing, so that we can only speak of the distance between them at a given time. If you are in a train traveling towards Edinburgh, we can speak of your distance from Edinburgh at a given time. But as we said, different observers will judge differently as to what is the same time for an event in the train and an event in Edinburgh. This makes the measurement of distances relative, in just the same way as the measurement of times has been found to be relative. We commonly think that there are two separate kinds of interval between two events, an interval in space and an interval in time. Between your departure from London and your arrival in Edinburgh, there are 400 miles and 10 hours. we have already seen that another observer will judge the time differently. It is even more obvious that he will judge the distance differently. An observer in the sun will think the motion of the train quite trivial, and will judge that you have traveled the distance traveled by the Earth in its orbit and its diurnal rotation. On the other hand, a flea in the railway carriage will judge that you have not moved at all in space, but have afforded him a period of pleasure which he will measure by his proper time, not by Greenwich Observatory. It cannot be said that you or the sun-dweller or the flea are mistaken. Each is equally justified, and is only wrong if he ascribes an objective validity to his subjective measures. The distance in space between two events is, therefore, not in itself a physical fact. But as we shall see, there is a physical fact which can be inferred from the distance in time together with the distance in space. This is what is called the interval in space-time. Taking any two events in the universe, there are two different possibilities as to the relation between them. It may be physically possible for a body to travel so as to be present at both events, or it may not. This depends upon the fact that no body can travel as fast as light. Suppose, for example, that it were possible to send out a flash of light from the Earth and have it reflected back from the Moon. The time between the sending of the flash and the return of the reflection would be about 2.5 seconds. No body could travel so fast as to be present on the Earth during any part of those 2.5 seconds, and also present on the Moon at the moment of the arrival of the flash, because in order to do so, the body would have to travel faster than light. But theoretically, a body could be present on the Earth at any time, before or after those 2.5 seconds, and also present on the Moon at the time when the flash arrived. When it is physically impossible for a body to travel so as to be present at both events, we shall say that the interval between the two events is space-like. When it is physically possible for a body to be present at both events, we shall say that the interval between the two events is time-like. When the interval is space-like, it is possible for a body to move in such a way that an observer on the body will judge the two events to be simultaneous. In that case, the interval between the two events is what such an observer will judge to be the distance in space between them. When the interval is time-like, a body can be present at both events. In this case, the interval between the two events is what an observer on the body will judge to be the time between them. That is to say, it is his proper time between the two events. There is a limiting case between the two, when the two events are parts of one light flash, or as we might say, when the one event is the seeing of the other. In that case, the interval between the two events is 0. There are thus 3 cases. 1. It may be possible for a ray of light to be present at both events. This happens whenever one of them is the seeing of the other. In this case, the interval between the two events is 0. 2. It may happen that no body can travel from one event to the other, because in order to do so, it would have to travel faster than light. In that case, it is always physically possible for a body to travel in such a way that an observer on the body would judge the two events to be simultaneous. The interval is what he would judge to be the distance in space between the two events. Such an interval is called space-like. 3. It may be physically possible for a body to travel so as to be present at both events. In that case, the interval between them is what an observer on such a body will judge to be the time between them. Such an interval is called time-like. The interval between two events is a physical fact about them, not dependent upon the particular circumstances of the observer. There are two forms of the theory of relativity, the special and the general. The former is in general only approximate, but is exact at great distances from gravitating matter. When the special theory can be applied, the interval can be calculated when we know the distance in space and the distance in time between the two events, estimated by any observer. If the distance in space is greater than the distance that light would have traveled in the time, the separation is space-like. Then the following construction gives the interval between the two events. Draw a line AB as long as the distance that light would travel in the time. Round A, describe a circle whose radius is the distance in space between the two events. Through B, draw BC perpendicular to AB, meeting the circle in C. Then BC is the length of the interval between the two events. When the distance is time-like, use the same figure, but let AC be now the distance that light would travel in the time, while AB is the distance in space between the two events. The interval between them is now the time that light would take to travel the distance BC. Although AB and AC are different for different observers, BC is the same length for all observers, subject to corrections made by the general theory. It represents the one interval in space-time, which replaces the two intervals in space and time of the older physics. So far, this notion of interval may appear somewhat mysterious, but as we proceed it will grow less so, and its reason in the nature of things will gradually emerge. But we'll have to wait for that emergence for another evening, because we've reached the conclusion of Chapter 4, which seems as good a place as any to end this evening's reading from the ABC of Relativity by Bertrand Russell. I'd like to say that cleared up a lot for me, but that might be pushing it. If you'd like to read this work for yourself, as always, you'll find a link to a free ebook from Project Gutenberg in the show description. If you'd like to connect or suggest a boring book you'd like to hear read, please drop me an email via our website, www.boringbookspod.com. It's always a pleasure to hear from you. Thank you so much for joining me for this evening's reading. Until our next boring book, good night.